Welcome to the deep dive. Ever looked up at a plane and just wondered, what kind of amazing engine is keeping that thing up there?
It's a great question.
Today, we're really digging into aircraft engines, figuring out exactly how they get that massive force needed for flight.
Exactly. And whether you're already deep into aviation or maybe just curious about the tech, we've sifted through some pretty detailed chapter excerpts. Our aim is to pull out the key ideas and, hopefully some things you might find quite surprising.
And we'll try to keep it clear, right? Not too much heavy jargon.
That's the plan.
Great. So our mission, if you will, is to pull out that core knowledge, those unexpected facts about aircraft engines from the stuff we've read. Think of it as your fast track to understanding what makes these things fly. Okay, let's jump in.
All right. So at its most basic level, an aircraft flies because of thrust. That's the force pushing it forward.
And how does it get that thrust?
By moving a working fluid, which, well, for almost all planes, is just the air around it, accelerating it backwards.
And that brings us to Newton's third law, doesn't it? That whole action-reaction thing.
Precisely. The engine throws air backwards. That's the action. And the reaction is the equal force pushing the aircraft forwards.
Now, I think a lot of people imagine the air being pushed out is sort of pushing against the air behind the plane.
Yeah, that's a really common misconception. But it's not quite right.
How so?
Think about a rocket in space. There's no air up there, right?
Yeah.
It's a vacuum.
Right, nothing to push against.
Exactly. But rockets still generate incredible thrust. They do it by throwing their own burned fuel, their combustion products, out the back at high speed.
So they don't need an external medium like air to push on.
Not at all.
Yeah.
So while most planes use the atmosphere, rockets carry their own fuel and the oxidizer to burn it. They're self-contained in that sense.
Okay, got it. So moving on from thrust itself, let's talk power. We hear horsepower a lot with car engines. Is it the same for planes?
It's interesting. The end goal for any aircraft engine, piston or turbine, is always thrust. But how we rate them, well, that differs. Your typical piston engine, like in a smaller plane, that's usually rated in brake horsepower, BHP.
Okay, BHP for piston engines. What about the big jet engines on airliners?
That's where we talk about thrust horsepower, or THP.
Thrust horsepower, is it a simple conversion?
Not quite. The sources give a formula. PHP equals thrust in pounds times the plane speed in miles per hour, then divide all that by 375.
375, what's that?
It's basically just a conversion factor that makes the units work out correctly between force, distance, time, and power.
Okay, so why use THP at all? Why not just stick with horsepower like cars?
We'll look at that formula again. The horsepower equivalent for a turbine actually changes with the aircraft's speed.
I see. So the THP number would be different at takeoff speed versus cruising speed.
Exactly. Thrust itself is a much more constant measure for these engines across different flight conditions, so it's just more practical to rate them in pounds of thrust.
That makes a lot more sense. The sources also mentioned something about how hard these engines work, percentage-wise.
Oh, yeah. Aircraft engines, especially during takeoff, are operating at a very high percentage of their maximum capability, usually full power.
Wow. For how long, typically?
Takeoff power is usually pretty short, maybe just a minute or two. Enough to get airborne safely.
Yeah.
Then power is reduced for the climb, and then pulled back quite a bit more for efficient cruising.
And engine weight came up, too. Something about power-to-weight ratio.
Usually important. It's often called specific weight, how much the engine weighs compared to the power or thrust it produces. Every pound you save on the engine is a pound you can use for fuel, passengers, cargo.
Or just better performance overall, right? Lighter means more agile.
Absolutely. Minimizing engine weight is a constant goal in design. It directly impacts the aircraft's useful load and how well it flies.
Okay, thrust, power, weight. Got it.
Yeah.
What about fuel economy? That's got to be huge, especially for airlines.
Critical. And the main way we measure that is specific fuel consumption. Basically, how much fuel the engine burns to produce a certain amount of power or thrust.
How is it measured for, say, a jet engine?
For gas turbines, it's thrust-specific fuel consumption, or TSFC. That's typically pounds of fuel burned per hour divided by the pounds of thrust the engine is producing.
And for the piston engines we talked about earlier?
For those, it's brake-specific fuel consumption, BSFC. Similar idea. Pounds of fuel per hour, but this time divided by the brake horsepower.
And turboprops?
They have a similar measure too, sometimes called equivalent-specific fuel consumption, accounting for both prop thrust and jet thrust.
So how do these different types stack up? Is one always better?
It really depends on the speed. What's interesting is that at lower speeds, maybe below 250 miles per hour or so, piston engines and turboprops are generally more fuel efficient.
More efficient than jets. Why?
Well, jets become efficient at higher speeds, but below that, propellers are pretty good. However, once you get much above, say, 400 mile per hour, propeller efficiency starts to drop off quite sharply.
Why does that happen?
The tips of the propeller blades start getting close to the speed of sound, creates a lot of drag, shock waves, becomes very inefficient.
Ah, okay. So that's why high-speed airliners use turbofans.
Exactly. Turbofans are optimized for those higher subsonic speeds where propellers struggle. It really shows you need to match the engine type to the mission profile.
Makes sense. Now, beyond just sipping fuel, these engines have to be unbelievably reliable. Failure isn't really an option.
Absolutely not. The sources make a clear distinction between reliability and durability, though they're linked. Reliability is usually measured as mean time between failures MTBF. Basically, how long, on average, does it run before any kind of malfunction happens?
Okay, MTBF. And durability.
Durability is more about the planned lifespan, often measured as mean time between overhauls or TBO. How long can it run before it needs a major scheduled disassembly, inspection, and rebuild?
So who ensures these things meet the standard? It sounds like a big responsibility.
It is. It's a team effort, really. You've got regulatory bodies like the FAA setting the bar. Then the engine manufacturer has a massive role design, R&D, incredibly rigorous testing, quality control during manufacturing.
And the company building the plane itself?
The airframe manufacturer is involved too, integrating the engine and ensuring the whole package meets the safety standards. The engine maker does exhaustive tests before an engine even leaves the factory.
And durability, the TBO, is that set in stone once the engine is designed?
Not entirely. The manufacturer provides a recommended TBO based on testing and expected conditions. But the actual time an engine achieves between overhauls can vary a lot. It really depends on how it's operated.
Like how?
Things like how often it's run at high power, the temperatures it experiences, the quality of maintenance, how well it's looked after. Consistent, high-quality maintenance is key.
So it's not just build it and forget it.
Definitely not. Continued reliability and durability depend heavily on ongoing maintenance, regular inspections to catch small things early, and pilots sticking to the operating limits set by the manufacturer.
Okay. The sources also mentioned operating flexibility and compactness. What do those mean in this context?
Operating flexibility is about how well the engine performs across its whole operating range, different speeds, different altitudes, different temperatures.
So it needs to work just as well taking off from a hot desert runway as it does cruising at 35,000 feet where it's freezing.
Exactly. Smooth, reliable power delivery under all those conditions.
And compactness. Seems obvious that smaller is better, but why specifically?
Several reasons. A smaller engine allows for a more aerodynamic nacelle or cowling, which means less drag.
Better fuel economy again.
Right.
Yeah.
It also helps with aircraft balance and weight distribution. For single-engine planes, a smaller engine up front can mean better visibility for the pilot. And fundamentally, compactness usually ties into lower weight. A bulky engine is often a heavy engine.
So putting all this together, speed, efficiency, weight, reliability, cost, probably. How do manufacturers actually choose an engine for a new plane design?
That's the power plant selection process. It's a huge decision. Our sources give some general rules of thumb, mostly based on the planned cruising speed.
Like what?
For planes cruising below, say, 250 mile per hour, you're often looking at a reciprocating engine. They're generally cheaper and quite efficient at those lower speeds. If you need better high-altitude performance, you might add a turbocharger or supercharger to that piston engine.
Okay, what about faster planes?
Move up to the 180 to maybe 350 mile per hour range, and turboprops become very attractive. They offer a better power-to-weight ratio than piston engines, which is great for carrying more payload or fuel.
And for the airliners we see every day.
Right, for speeds from around 350 mile per hour up to Mach 0.8, 0.9, that's typical airline cruising speed, the turbofan is king. It offers the best blend of efficiency and speed in that range.
What about going even faster, supersonic?
For Mach 1 and above, you're generally talking pure turbojets, maybe with afterburners for extra thrust, or sometimes specially designed low-bypass turbofans.
And I guess cost is always lurking in the background.
Always. Gas turbine engines, turboprops, turbofans, turbojets, they offer amazing performance, but they are significantly more expensive to buy and maintain than reciprocating engines. So cost is often a major deciding factor, especially for smaller aircraft.
Okay, let's dive deeper into the piston engines first. The sources mention different ways they're classified.
Yeah. mainly by how the cylinders are arranged. You've got inline engines, like in many older cars, with cylinders in a row, V-type, where they form a V, radial engines, common on older propeller planes, with cylinders in a circle around the crankshaft, and opposed engines, where cylinders lie flat on opposite sides, very common in general aviation today.
And also by how they're cooled, air or liquid?
Right, air-cooled or liquid-cooled. Though it's worth remembering that even liquid-cooled engines ultimately dump their heat into the air via a radiator. So in a way, all aircraft engines are air-cooled eventually.
So what's the functional difference then?
Air-cooled engines have those visible fins on the cylinders. The fins increase the surface area, so heat can transfer directly to the airflow passing over them.
Simple enough.
Liquid-cooled engines circulate a coolant like antifreeze in a car through passages in the engine block and cylinder heads. This hot liquid then goes to a radiator where air flows through it, cooling the liquid before it circulates back.
Any advantages to liquid cooling?
It can be more effective at removing large amounts of heat, especially for very high-power engines packed into tight spaces. But it adds weight and complexity. The coolant itself, the radiator, pumps, plumbing.
Whereas air cooling is lighter and simpler.
Generally, yes, but maybe less effective in some high-power or restricted airflow situations.
Okay, let's break down a typical reciprocating engine. What are the absolute core parts we need to know?
You've got the crankcase, it's the main body or foundation. The cylinders, where the action happens, pistons moving up and down inside the cylinders.
Connected by?
Connecting rods. They link the piston to the crankshaft. The crankshaft is the piece that turns the up and down motion into rotation.
Got it. What else?
Valves, intake, and exhaust valves in each cylinder head to let the fuel air mix in and the burnt gases out. And a mechanism to open and close those valves at exactly the right time. Plus, spark plugs to ignite the mix.
Let's zoom in on some of those. The crankcase sounds like more than just a box.
Oh, definitely. It's the structural core. It holds the crankshaft steady in its bearings, keeps the lubricating oil contained, provides mounting points for the cylinders, and it's how the whole engine bolts onto the airplane.
So it has to be really strong and rigid.
Extremely. Made usually from aluminum alloy castings or forgings.
Uh-huh.
It's taking all the forces from combustion, the spinning crankshaft, propeller loads. It has to hold everything in perfect alignment.
And how do the cylinders attach?
They bolt onto precisely machined pads on the crankcase, usually with strong studs and nuts. There's often a seal, like an O-ring, to prevent oil leaks there.
You mentioned radial engines earlier. Does the crankcase differ much for them?
Radials often have distinct sections. A nose section might house propeller gearing and bearings. A power section holds the cylinders. And a rear section, the accessory section. Some even have a small oil sump built into the nose section.
Accessory section, what's that for?
Usually at the very back is a housing, often magnesium or aluminum alloy, that provides mounts for all the engine-driven accessories.
Like the ignition system.
Exactly.
Mm-hmm.
Magneos for ignition, fuel pumps or carburetors, oil pumps, starter, generator. All that stuff bolts onto the accessory section and is driven by gears connected to the crankshaft.
Okay, the crankshaft, the backbone. How does it actually turn piston movement into rotation?
It has offset sections called throws or crank pins. The connecting rod from each piston attaches to a crank pin. As the piston pushes the rod down, the offset makes the crankshaft rotate.
What's it made of? Looks heavy duty.
It is, usually forged from incredibly strong chromium nickel molybdenum steel. It has main journals that sit in the main bearings in the crankcase, the crank pins where the rods attach, and crank cheeks connecting them.
And it has to be perfectly balanced, I imagine.
Critically important. They use counterweights, sometimes internal dampers, to smooth out vibrations from all those parts moving. It needs both static balance, like balancing a tire, and dynamic balance, ensuring it runs smoothly when spinning fast.
Right. And the connecting rods linking the pistons to those crank pins, are they all the same?
Not quite. The simplest are plain rods, used in inline and opposed engines. Some older V engines used fork and blade rods, where one rod straddled the other on the same crank pin.
And radials. They look complicated.
They use a master and articulated rod system. One cylinder has a big master rod connected directly to the crank pin. The rods for the other cylinders in that row, the articulated rods, connect to pivot points or knuckle pins on the master rod.
Wow, okay. What about the pistons themselves, taking all that heat and pressure?
They're amazing pieces, usually forged aluminum alloy. They have grooves for the piston rings, often internal fins for cooling. The top, the head, can be flat, domed, or dished, sometimes with cutouts for valve clearance.
I read something about campground pistons.
Yeah, that's clever. They make the piston slightly oval-shaped when cold. As it heats up and expands, it becomes perfectly round, giving a better fit in the cylinder and reducing piston slap during warm-up.
And the pin connecting the piston to the rod.
The piston pin, or wrist pin, it's usually full floating, meaning it can rotate in both the piston and the connecting rod. Little aluminum plugs at the ends stop it sliding sideways and scratching the cylinder wall.
And the rings fitted around the piston. Tiny parts, big job.
Absolutely crucial. They do two main things. Seal the combustion pressure above the piston, preventing blow-by into the crankcase, and control the oil film on the cylinder wall, scraping excess oil back down.
What are they made from?
Mostly high-grade cast iron. Sometimes the top compression ring might be chrome-plated steel for extra wear resistance, but you have to be careful you never use chrome rings in a chrome-plated cylinder barrel.
Why not?
They won't seat properly. They'll just skate on each other. You need one surface to wear slightly to conform to the other. So chrome ring with steel barrel or cast iron rings with chrome barrel is okay.
Gotcha. Okay, the cylinders. Where the power is actually made, what are the key parts?
Two main parts usually. The cylinder head, typically aluminum for good heat dissipation, bolted or screwed onto the cylinder barrel, which is usually high-strength steel to handle the pressure and wear.
How do they join them? Seems like a critical seal.
Often they heat the aluminum head to expand it, chill the steel barrel to shrink it slightly, and then screw them together very tightly. When they reach operating temperature, the different expansion rates make the joint even tighter.
Clever. What's inside the head?
The combustion chamber shape, ports for the intake and exhaust valves, spark plug holes, and the valve operating mechanism parts, valve guides, valve seats, rocker arm supports.
Valve seats?
Yeah, hardened metal rings pressed into the head where the valves seal against. They have to withstand constant pounding and high heat.
And the barrel. Just a smooth tube.
It has to be incredibly strong and wear-resistant, usually steel alloy forgings. The inside surface is hardened, often by nitriding, or sometimes chrome plating for repairs. Then it's honed to a very precise finish with a slight crosshatch pattern to help the rings seat and hold oil.
I saw mention of choked cylinders.
Yeah, some are made slightly narrower at the top, the head end, when cold. Because the head runs hotter, it expands more, so the choke ensures the barrel becomes perfectly straight at operating temperature.
Okay, the valves themselves, letting gases in and out.
Usually poppet valves, mushroom, or tulip-shaped. Intake valves run cooler, maybe made of chromic nickel steel. Exhaust valves see extreme heat, so they use tougher stuff like nichrome or sochrome, maybe cobalt chromium alloys.
I heard some are filled with sodium.
That's right. High-performance exhaust valves often have hollow stems filled with metallic sodium. The sodium melts, sloshes around inside, and transfers heat from the hot valve head down the stem where it can be cooled better. Need to handle them carefully if damaged, though.
And how do these valves know when to open and close?
That's the job of the valve operating mechanism. It's all about timing. Controlled by a camshaft or cam ring.
Camshaft, like in a car.
Exactly, for inline and opposed engines. A rotating shaft with lobes that push on lifters or tappets. Radial engines often use a cam ring with lobes on its face that rotates around the crankshaft.
And these push?
Tappets then usually push rods up to rocker arms mounted on the cylinder head, which then push the valve stems down to open the valves against spring pressure.
Sounds complex. Does it need constant adjustment?
Older designs did. But many modern engines use hydraulic valve lifters, or tappets, that use engine oil pressure to automatically take up any clearance, keeping things quiet and maintenance-free in that respect.
I saw valve overlap mentioned. What's that?
That's a short period, right at the end of the exhaust stroke and beginning of the intake stroke, where both the intake and exhaust valves are slightly open simultaneously.
Why do that? Seems counterintuitive.
It actually helps. The outflowing exhaust helps pull the fresh intake charge into the cylinder, improving filling. It also helps scavenge out the last of the burnt gases and provide some cooling.
Fascinating. Okay, bearings. Keeping everything spinning freely, what types are used?
Several types. Plain bearings, basically a highly polished shaft journal running in a softer bearing shell with a film of oil in between, are used for crankshaft mains, connecting rods, camshafts. They handle radial loads well.
What about other loads?
Roller bearings, using cylindrical or tapered rollers, are used for higher loads or where you need to handle thrust axial loads too. Ball bearings are also common, handling both radial and thrust loads, often used for accessory drives and propeller thrust bearings in radials.
And propeller reduction gearing. Why slow the propeller down?
Because engines often develop peak power at high RPM, but propellers are most efficient at lower RPMs. If the prop tips go supersonic, efficiency plummets and noise skyrockets. The reduction gear lets the engine spin fast while the prop spins slower and more efficiently.
How does it work? Like a car gearbox.
Sort of. Common types are planetary gear sets, like in an automatic transmission using a central sun gear surrounding planet gears and an outer ring gear to achieve the reduction. Spur planetary is common.
And finally, connecting the prop to this gearbox, or the engine, the propeller shaft.
Right. Older, smaller engines might use a tapered shaft with a key. Higher power radials often use spline shafts for strength. But most modern reciprocating and turboprop engines use a flange shaft, a flat plate on the end of the shaft that the propeller bolts directly onto.
Wow, that's a lot of intricate parts working together. Now, how does it actually make power, the four-stroke cycle?
Exactly. Most aircraft reciprocating engines operate on the four-stroke cycle, often called the Otto cycle. 4 strokes of the piston for one complete power cycle.
Which takes how many turns of the crankshaft?
2 full revolutions, 720 degrees.
Okay, walk me through the strokes.
First is the intake stroke. Piston moves down, the intake valve opens, and the fuel-air mixture is drawn into the cylinder. The intake valve actually opens a bit before the piston reaches the top. That's valve lead. Compression. Piston moves up, both valves are closed, squishing that mixture and raising its temperature and pressure. Near the top of this stroke, usually 20-35 degrees before top dead center, the spark plugs fire. That's ignition timing.
Why fire before the top?
Takes a fraction of a second for the flame to spread. Firing early ensures peak pressure happens just as the piston starts moving down on the power stroke.
Which is stroke number 3.
Right. Power. The burning, expanding gases force the piston down powerfully. This is what turns the crankshaft and produces power. Both valves stay closed.
And finally,
exhaust. Piston moves back up. The exhaust valve opens, pushing the burned gases out of the cylinder. The exhaust valve usually stays open a little bit after the piston passes the bottom, that's valve lag, to help clear the cylinder. Then the intake opens again, and the cycle repeats. We mentioned valve overlap earlier. That happens between exhaust and intake.
Got it. Intake, compression, power, exhaust. Over and over. Now, how do we quantify the power these engines make?
Okay, physics basics first. Work is force times distance. Like lifting 1 pound, 1 foot is 1 foot-pound of work. Power is the rate of doing work.
And horsepower.
James Watt figured 1 horse could do about 33,000 foot-pounds of work per minute, or 550 per second. That became the standard unit, horsepower.
How does that relate to the engine?
We need to know a few things. Piston displacement, that's the volume the piston sweeps inside the cylinder, calculated from the cylinder's bore area, times the piston's stroke distance. Total engine displacement is that volume times the number of cylinders.
Okay, displacement, like liters or cubic inches in a car?
Exactly. Then there's compression ratio, the ratio of the cylinder volume when the piston's at the bottom, PDC, versus when it's at the top, PDC. Higher compression generally means more power and efficiency, but there are limits based on fuel octane and engine design.
Right, so how do we get to horsepower?
First, there's indicated horsepower. This is the theoretical power developed inside the cylinders, calculated using a formula called Playanc. It involves pressure, effective pressure inside, length of stroke, area of the piston, number of power strokes per minute, and number of cylinders.
Theoretical, meaning not what you actually get out.
Correct. Because some power is lost to pistons rubbing, bearings spinning, gears meshing, all that internal resistance.
So the actual usable power is?
Brake horsepower,
yeah.
bhp. That's the power actually delivered to the propeller shaft, measured experimentally using a device like a dynamometer or, historically, a Prony brake, which measures the engine's torque, twisting force. bhp is what manufacturers usually quote.
And the difference between FBP and bhp?
That's friction horsepower, FHP, the power lost overcoming internal friction. So IAP equals bhp plus FHP.
Makes sense. I saw terms like BMEP, too.
Right. Brake mean effective pressure. It's a useful theoretical pressure that relates directly to bhp. It's like asking what constant pressure, if applied to the pistons during the power stroke, would produce the measured brake horsepower. It's a good way to compare the breathing and efficiency of different engines, independent of size or speed.
Okay. And we already mentioned thrust horsepower.
Yeah, the OP is the power actually converted into forward thrust by the engine and propeller working together. It's always less than bhp because propellers aren't 100% efficient. The typical propeller might be around 80% efficient.
So lots of ways to measure power. What about efficiency? How much of the fuel's energy actually becomes useful work?
That's thermal efficiency. It's the ratio of the work done, either indicated or brake horsepower, to the heat energy released by burning the fuel.
And how good are these engines?
Reciprocating engines are actually not that efficient thermally, maybe around 30-34% brake thermal efficiency. A huge amount of the fuel's energy is lost as heat out the exhaust, heat rejected to the cooling system, and friction.
Wow, only about a third becomes useful power.
Roughly, yeah.
Yeah.
Those sources give breakdowns like maybe 40% lost in exhaust, 15% to cooling, 5–10% to friction. Only leaves about 30–35% for BHP.
What other efficiencies matter?
Mechanical efficiency is the ratio of BHP to HP. Basically, how much of the power developed in the cylinders makes it to the shaft. Usually pretty high, around 90%, mostly affected by friction. Volumetric efficiency is about how well the cylinders fill with fuel-air mixture during the intake stroke. A 100% efficient engine would draw in a volume exactly equal to its displacement.
But it's usually less.
Often less, yeah. Things like throttling the engine, intake type restrictions or bends, high air temperatures, or poor exhaust scavenging can all reduce it. Supercharging, though, can push it over 100%.
And propeller efficiency.
We mentioned that, also called propulsive efficiency, ratio of thrust horsepower to brake horsepower. Usually around 80%, maybe 85% max, heavily dependent on the propeller design and how its blade angle is controlled, especially with constant speed props.
Okay, that's a deep dive into reciprocating engines. Now, let's shift gears to the other major type. Gas turbines. Fundamentally different, you said.
Totally different concept and operation. Instead of the 4 strokes happening sequentially in one cylinder, a gas turbine has separate sections for intake, compression, combustion, and exhaust, and the process happens continuously and simultaneously in those sections.
A continuous flow of power.
Exactly.
And the main types again?
Turbofan, turboprop, turboshaft, and the original turbojet.
Turbojets aren't that common anymore, right?
Not for most commercial planes, no. They're noisy and relatively fuel-hungry at subsonic speeds. Turbofans really dominate airliners now. That big fan at the front bypasses a lot of air around the core engine, providing most of the thrust, like 80%, sometimes much more quietly and efficiently.
Some have multiple shafts, I read. Spools.
Yeah, complex turbofans often have 2 or even 3 concentric shafts, or spools, connecting different compressor and turbine sections that spin at different optimal speeds. A low-pressure spool, fan and rear turbine stages, and a high-pressure spool, core compressor and initial turbine stages.
And turboshafts.
They're designed to deliver power to a shaft, not primarily produce thrust. Perfect for helicopters, also used as auxiliary power units, APUs, on big planes.
And turboprops are like a jet engine driving a propeller.
Pretty much. A gas turbine spins a propeller through a reduction gearbox. They get most of their thrust from the prop, though the exhaust adds a bit too.
Okay, let's break down the gas turbine, starting at the front.
Yeah.
The air entrance, or inlet.
Critical piece. Its job is to capture air smoothly and deliver it to the compressor with minimal energy loss or turbulence. The inlet shape heavily influences how much pressure builds up just from the forward motion of the aircraft, the ram effect, and affects compressor efficiency.
Does the inlet design change much?
Oh yeah. A big turbofan inlet looks very different from one on a turboprop or a military fighter. Turbofan inlets need anti-icing, maybe noise reduction liners. Turboprops might have screens or deflectors for debris. Supersonic inlets use complex ramps and shapes to slow the air down effectively before it hits the compressor.
Then the accessory section, similar to the piston engine.
Similar purpose, yeah. Housing and drive gears for fuel pumps, oil pumps, starter generators, etc., usually driven off the main engine shaft via a gearbox. Sometimes it doubles as the oil tank.
Next up, the compressor. What's its main job?
Its primary job is to take the low-pressure inlet air and squeeze it, dramatically increasing its pressure before it goes into the combustor. This high-pressure air is key for efficient combustion.
Does it do anything else?
Secondary job is providing bleed air, tapping off some of that high-pressure air for other systems, cabin pressurization, anti-icing, engine starting, sometimes even powering air-driven units or systems to blow debris away from the inlet on the ground.
Are there different kinds of compressors?
2 main families, centrifugal flow and axial flow.
Centrifugal, like spinning something outwards.
Exactly. It uses a rotating impeller that slings the air outwards at high speed. Then a surrounding diffuser section slows the air down, converting that speed into high pressure.
Pros and cons.
Pros. High pressure rise per stage, efficient over a wide speed range, relatively simple, light, and easy to start. Cons. Larger frontal area for the airflow handled, some efficiency losses in the turns the air has to make.
And axial flow.
This uses multiple stages of rotating blades, rotors, and stationary vanes, stators, arranged along a shaft. Air flows straight through, axially. Each stage adds a bit more pressure. You often see inlet guide vanes at the front to direct air properly onto the first rotor stage.
How are the blades held on? Seems like a high-stress job.
Rotors can be drum type or, more commonly in high-speed engines, disc type. Blades attached to the discs using strong root designs, like fir tree or bulb shapes, that slide into the disc rim.
And the pros and cons of axial.
Pros: very high peak efficiency, small frontal area for high airflow, straight through flow, can achieve very high overall pressure ratios with multiple stages. Cons: efficiency drops off outside their optimal speed range, much more complex and expensive, generally heavier, needs more power to start.
Okay, after the compressor, you mentioned a diffuser.
Right. It's basically a diverging duct. It slows down the high-speed air coming out of the compressor, which further increases its static pressure just before it enters the combustion section. You want relatively slow, high-pressure air for good burning.
Makes sense. Now the combustion section, the hot part.
This is where the fuel gets added to that high-pressure air and burned. The goal is to add a massive amount of heat energy to the air, raising its temperature dramatically.
What are the key bits inside?
You need an outer casing to contain the pressure, an inner liner, usually full of holes and scoops where the burning actually happens, fuel injectors to spray fuel in, igniters, like spark plugs but only needed for starting, and a drain to get rid of unburnt fuel after shutdown.
Are there different layouts?
Yeah, 4 main types described in the sources. Can type, individual cans like on older engines or APUs. Can annular, individual flame tubes inside an annular casing, less common now. Annular, a single ring-shaped liner, very common in modern engines. And reverse flow, air doubles back, used to make engines shorter.
How does the air actually burn cleanly in there?
The liner design is key. Only some of the air, primary air, mixes directly with fuel for initial burning. Lots more air, secondary or dilution air, flows through other holes in the liner to cool the liner itself, complete the combustion, and lower the gas temperature before it hits the turbine.
Okay, super hot gas leaves the combustor and hits the turbine section. What happens here?
The turbine's job is to extract energy back out of that hot, high-pressure gas flow. This energy is used to spin the compressor, they're on the same shaft, and also drive the accessories.
How much energy does the compressor take?
A lot. In the core engine, maybe 2/3 or even more of the turbine's energy output goes right back into driving the compressor. It takes a huge amount of power to compress all that air.
So what's left over?
The remaining energy in the gas flow either provides direct thrust out the back in a turbojet, or it drives additional turbine stages connected to the fan, turbofan, or propeller gearbox, turboprop, or output shaft, turboshaft.
What are the main parts of the turbine section?
2 key elements per stage: stationary turbine inlet guide vanes, also called nozzle guide vanes or stators, and the rotating turbine wheel itself, which is a disc with blades attached.
What do the guide vanes do?
They take the hot gas from the combustor, accelerate it, and direct it onto the moving turbine blades at the perfect angle to make them spin efficiently.
And the blades must be under incredible stress.
Unbelievable conditions.
Yeah.
Extreme heat, huge centrifugal forces. They're made from exotic nickel-based superalloys, often directionally solidified or even grown as single crystals to eliminate weak points. Many are hollow with intricate internal passages for cooling air bled from the compressor. Some have thermal barrier coatings.
How are they attached to the disc?
Again, usually with fir tree or similar interlocking root designs, often held in place with tabs or rivets. Some are even integrally cast with the disc, blisks.
Can there be multiple turbine stages?
Oh yes. Simple turbojets might have 1 stage. But engines driving heavy loads, big fans, props, multiple compressor spools will have multiple turbine stages, each extracting more energy. You'll have high-pressure turbines driving the high-pressure compressor and low-pressure turbines driving the low-pressure compressor or fan prop.
Okay, after the last turbine stage, we get to the exhaust section.
Right. Its job is to collect the hot gases, straighten the flow, and accelerate them out the back through a nozzle to produce thrust efficiently.
What's in there?
Usually starts with an exhaust cone to collect the flow smoothly, might have struts inside, then maybe a tailpipe if needed, and finally the exhaust nozzle itself.
What shape is the nozzle?
For subsonic flight, it's typically a convergent nozzle. It narrows down to speed up the flow. For supersonic flight or engines with afterburners, you need a convergent-divergent CD nozzle to accelerate the flow beyond Mach 1.
Any other features in the exhaust?
You'll find mounts for temperature probes, thermocouples, sometimes insulation blankets to protect the aircraft structure from the heat. Variable area nozzles are common on afterburning engines to optimize performance, whether the afterburner is on or off.
And bearings and seals, critical for these high-speed rotating parts too, I assume.
Absolutely. Main rotor bearings support the shafts, usually a mix of ball bearings, handling thrust and radial loads, and roller bearings, mainly radial loads. Multi-spool engines need bearings between the spools too. They're lubricated by pressurized oil jets and protected by complex seals, often labyrinth seals that use air pressure and tight clearances rather than physical contact.
Okay, we've covered the main components. Let's quickly revisit the specific engine types again. Turboprop.
Gas turbine core plus extra turbine stages driving a reduction gearbox which turns a propeller. Most thrust from the prop can be fixed turbine, compressor and prop turbine linked, or free turbine. Prop turbine spins independently.
Turboshaft.
Similar. But power goes to a shaft output, usually for a helicopter transmission or APU generator, measured in horsepower. Often uses a free turbine.
And turbofan the airliner engine.
Think of it like a turboprop with a ducted fan instead of a propeller. Fan can be part of the first compressor stage or separate. Fan moves huge amounts of air, most of it bypassing the core. Extra turbine stages drive the fan. Gets great thrust and efficiency at high subsonic speeds. Exhaust from the core and fan can be mixed or exit separately.
Right. Now, let's nail down thrust generation again for these turbines. How does accelerating air backwards make thrust?
It's Newton again. Second law this time. Force equals mass times acceleration, FMA. The engine takes in a mass of air, m, and accelerates it from its entry speed, aircraft speed v1, to a higher exit speed, v2. The change in momentum creates the force, or thrust.
The formula was
Net thrust,
FM.
mass flow rate, m's, times exit velocity v2 minus inlet velocity v1, all divided by g, the gravitational constant, just to keep the units consistent. Pounds of mass flow versus pounds of force.
So more thrust comes from moving more air, higher m's, or accelerating it more. Bigger difference between V2 and V1.
Precisely. Turbofans move a huge mass of air but don't accelerate it as much as a pure turbojet, which moves less air but accelerates it to much higher speeds. Different ways to achieve thrust.
Does aircraft speed affect thrust much?
It does, but it's complex. As aircraft speed, V1, increases, you might think thrust would dry because the V2, V1 term gets smaller. But increasing speed also tends to force more air into the engine, increasing M's, and can increase V2 as well, due to the ram effect. The net result is often relatively stable thrust over a range of speeds.
What about Bernoulli's principle? Air speeding up, pressure dropping.
That's happening all through the engine. Inlets and diffusers are divergent ducts. They slow the air to increase pressure. The compressor blades are shaped to increase pressure. The combustion chamber is roughly constant pressure. Turbine nozzles and the final exhaust nozzle are convergent ducts. They speed up the flow to decrease pressure and generate velocity thrust.
Okay, last big topic. What really drives the performance of these gas turbines? What makes one better than another?
Thermal efficiency is still key. How much fuel energy becomes useful work or thrust? And the sources highlight three really critical factors for that.
Which are?
1. Turbine inlet temperature, TAT. Hotter gas entering the turbine means more energy available. 2. Compressor pressure ratio. Squeezing the air more before combustion allows for higher efficiency. 3. Component efficiencies. How well the compressor actually compresses and the turbine actually extracts energy, aerodynamically speaking.
So hotter, higher pressure, and better aerodynamics are good.
Basically, yes. Though TIT is limited by material science, how hot can the turbine blades get before they melt or fail? There's always a trade-off between performance and engine life.
What else affects performance day to day, like weather?
Big time. Outside air temperature, OAT is huge. Colder air is denser, meaning more mass flow enters the engine for a given volume. Also, the engine doesn't have to work quite as hard to achieve the same pressure ratio if the air starts colder. So colder OAT generally means more thrust.
And altitude.
As you go higher, air gets colder, which helps a bit, but much less dense, which hurts a lot. The density effect wins out, so thrust decreases significantly with altitude.
What about airspeed's effect on thrust? We touched on it, but it sounded complicated.
It is. There's ram drag from shoving air into the inlet, which increases with speed and tends to reduce net thrust. But there's also ram recovery, the pressure rise in the inlet due to speed, which increases mass flow and helps boost thrust.
So they fight each other?
Kind of. At low speeds, the drag effect might dominate, causing thrust to dip slightly as speed increases from zero. But as speed builds, the ram recovery effect becomes stronger, forcing more air in and increasing thrust, especially at higher speeds, until you approach compressibility issues near Mach 1. The exact shape of the thrust curve depends on the engine type and design.
Wow. Okay, I think my head is full, but in a good way. That was an incredibly detailed look at both reciprocating and gas turbine engines.
Yeah, we covered a lot of ground, from the basic physics to the nitty-gritty components and performance factors.
So, quick recap. Thrust from pushing air back, Newton. Piston engines work in cycles: intake, compression, power, exhaust. Gas turbines work continuously: intake, compress, burn, exhaust turbine. Different ways to measure power: BHOT, a THB thrust. Efficiency depends on speed and engine type, TSFC, BSFC. Reliability and durability are paramount. And things like temperature, altitude, and speed have big impacts.
That sums it up pretty well.
Yeah.
Hopefully it gives everyone a much better sense of the engineering magic happening inside those engine pods.
Absolutely. So here's a final thought to chew on. We know aviation is always pushing for greater efficiency, less noise, lower emissions. Considering all the advances in materials and aerodynamics, maybe even alternative fuels, what do you think aircraft engines might look like or operate like in the next, say, 20 or 30 years? How different could they be?
That's the multi-billion-dollar question, isn't it? Definitely a field that's constantly evolving. And hey, if any specific part of this sparked someone's interest, compressors, turbines, combustion, there's so much more detail out there to explore.
For sure. Well, thank you for joining us on this deep dive into aircraft engines. We really hope you found it useful and maybe even a bit exciting.